Hi guys, we have thus far solved systems of two equations and two variables. Now we're going to solve systems of three equations and three variables. And we can use all the same techniques that we used for the other systems, it's just we have to be a little bit more careful with our accounting. And there's a slight twist with the elimination process, which I'll show you in just a second. So we can use substitution, we can use graphing, we can use elimination. We don't typically use graphing for solving systems that are more complicated than two equations and two variables. It gets a little cumbersome and really hard to draw the 3D graphs and get accurate solutions. It can be done, we're not going to do it. You're welcome. So, let's start with this first problem. Wait. Almost forgot the what-wa. Check out the what-wa. Solving systems are what? Is solving systems of three linear equations with three variables. How? We're going to do it algebraically with substitution and elimination. The applications are myriad, including programming, architecture, and finance. Not so much with theorems. And the why, well, the why is something I would like to hear about from you. I would like to see if you can figure out why we need to do this. What is your best guess? And I'd like to see it in your notes. Okay. So, let us begin, shall we? So this first system, three equations, three unknowns. And let's get a little bit larger, shall we? So we can use substitution or we can use elimination. Now this is a fairly simple system in that there are three variables. We have x, we have y, we have z, but they don't all appear in each equation. So this system is nicely set up for substitution. So why don't we substitute? I can rewrite this equation solving for x in terms of y, right? And why did I choose this particular equation? Why am I rewriting this one? Because look at that there. I don't like this. Here we go. Sorry. We have a coefficient of 1 on that x. So we don't have to do any funky dividing. There's no chance we're going to end up with some scary fractions. We just have to subtract 3y from both sides. And now we have an expression for x, right, in terms of y. We can substitute this anywhere we see x. Let's start with equation 3. Instead of 3x plus 4y equals 3, I'm going to use my new expression for x and say 3 times negative 3y minus 4 plus 4y equals 3 equals, equals 3. I'm pretty sure my stylus is getting low on juice. Hopefully we can finish before it dies. I'm going to distribute this 3 now to everything in the parentheses, right? Negative 9y minus 12 plus 4y equals 3. Negative 5y minus 12 equals 3. Negative 5y equals 15. This is a 3. And y equals negative 3. So we have a value for one variable. And we can use it in any of the three equations to find the other variables, right? So if we substitute negative 3 for y in, say, equation 1, instead of 2y minus 3z equals 0, we have 2 times negative 3 minus 3z equals 0. We get negative 6 equals 3z, and z equals negative 2. And in equation 2, we have x. Instead of x plus 3y equals negative 4, we have x plus 3 times negative 3 equals negative 4. X minus 9 equals negative 4, and x equals 5. So now we have an ordered triple, not an ordered pair. Now we have an ordered triple. And we're going to list these values alphabetically. So first I have my x is 5, My y is negative 3, and my z is negative 2. And that's by convention. There's no real solid, absolute, universal reason why we have to do it that way. It's just the way it's done. Okay, now if we were good soldiers, we would take these values, substitute them back into the system, and see that they work. We're not going to do that for this example, but we will for the next example. So now let's solve a system of 3 linear equations and 3 variables using elimination. And again, we do the same things with systems of 3 equations and 3 variables that we did for systems of 2. We first line up our variables and our constants, which we already have. And then we ensure that we have opposite coefficients on at least one variable, which we do. Again, nicely set up for us. We have already negative y here, positive y here, negative y here, right? So it's a negative 1 coefficient in equation 1. It's a positive 1 coefficient in equation 2, and a negative 1 coefficient in equation 3. So what we're going to do is combine equation 2 separately with equation 1 and equation 3. And this is key. You must use one equation twice. And for us, it's going to be equation 2 in this example. And we're going to talk in class about how to strategize, how to figure out what we want to use. It's going to take a little practice. It's actually not that tricky. Not for us. Okay, so I'm going to rewrite really the hardest part of these systems. They're not any more difficult than systems with 2 equations. The hardest part here is just the accounting. Don't lose sight of which equations you're combining, and don't lose your negative signs, and you should be fine. So first we're going to combine equations 1 and 2, which I will rewrite here. We just straight add these equations and we eliminate the y variable. We add our x's, we get 2x. We add our y's, we get 0y. We add our z's, we get 4z. And we add our constants and we get negative 4. Now we have a new equation, right? Which we're going to label equation number 4. So now let's combine equations 2 and 3. I'm going to rewrite both. And we can just straight add these. 3x plus 0y plus 5z equals negative 3. Brilliant. And we're going to call that equation 5. So now we have a new system of 2 equations with 2 unknowns. We have equation 4, which is in simplified form 2x plus 4z equals negative 4, and equation 5, which is in simplified form 3x plus 5z equals negative 3. So now what? What do we do now? Well, we solve this just like we've been solving them, right? What do you like, substitution or elimination? We could use either. I think I'm going to use substitution, because if I were to use elimination, I'm going to have to multiply both equations. And that just introduces a lot of opportunity for error. So instead, what I think I'm going to do is rewrite this guy in equivalent form. So if I were to solve equation 4 for x in terms of z, I would get 2x equals negative 4z minus 4. Divide both sides by 2, I get x equals negative 2z minus 2. And I can use this expression for x in equation 5. Let's do that, shall we? Okay. What is happening? Now, let me do this in steps. Okay, so now we have a value. Let's substitute that back into either equation 4 or 5 and see what we come up with. And I'm going to use, yes, yet another color. Well, green. And we have a second variable. Now, to get y, we're going to actually go way back up here to one of the original equations. I'm going to use equation 1. I have x minus y plus z equals negative 1. I don't like this thickness. Okay, substituting our values for x and z, we get 4 minus y minus 3 equals negative 1. We get 1 minus y equals negative 1. We get y equals 2. So our ordered pair then, our ordered triple is going to be 4, 2, negative 3. But we have to check. We've done a lot of manipulations, right? We've rewritten equations, we've substituted, we've blah, blah, blah. Look at all of these different lines, right? Lots of opportunity for error. So we have to check. And it's not a solution. This ordered triple is not a solution unless it is a solution for, okay, what am I going to do?